Now, the thing that's important to know is that the area ratio is the square of the linear ratio, and the volume ratio is the cube of the linear ratio. Okay, you understand why?
Yeah.
Okay, good. So I know that Yansack goes little to big, which I think is just horrible. Big to little makes so much more sense. But I don't want to confuse you. And I have a couple of Yansack students, so I figured I would force myself and go little to big. Okay? So let's do R sub L first. What's R sub L going to be? Find a linear measurement on the small triangle and compare it to this corresponding side on the other. It's linear because it's only in centimeters. It's not in square centimeters like area is going to be.
So 6 to 12?
1 to 2.
Yeah.
Okay. What's that make the area ratio equal to?
It would be 1 to 4.
Okay. And as long as we're here, let's do the volume ratio.
1 to 8.
Okay. Now, the thing they gave us was area. They gave us the area of the small triangle and they gave us the area of the big triangle. So what kind of, how can I figure out the area of the big triangle? Oh, hold on. Excuse me. They gave us the area of the big triangle. They want the area of the small triangle.
Yeah.
So what is it going to be?
Would you do like 1 over 4 equals x over 72?
Well, if you want to set up a ratio, then you can say 1 is to 4 as, let's see, the big goes on the bottom. So if I'm solving for x, that's the ratio I'm going to set up. X is basically going to be 1/4 of 72, right? In other words, if the area ratio is 1 to 4, then they're telling me the area is 72, the area of the smaller one must be 1/4 of 72. And that's what you get if you solve that. You get x equals 72 divided by 4. So you have a calculator, go ahead and figure out what that is and put it down there. I don't care so much about the answers as I do the method. Okay? And I'll explain to you why big to little is so much better than little to big when we get to a problem where it's appropriate. Okay, here again they give us the area ratio. So what's the linear ratio?
3 to 4.
Correct. So R sub L is the square root of the area ratio, and that's 3 to 4. What's the, okay, let me write the area ratio here. That's 9 to 16. What's the volume ratio?
It's 27 to 64.
64, exactly. Okay. So now they've given us, they want TR. Well, if you look at TR and compare it to LA, what kind of ratio? What's TR going to be?
Is it going to be linear or like RL?
What's it going to equal? What's the equation that it's going to equal?
Oh, it's going to equal 3/4.
Times?
Um,
That's the
X.
linear ratio. But we have to convert this 24-meter distance into an equivalent distance for TR. Well, if the linear ratio is 3/4, then I need to multiply 24 by 3/4, right?
Mm-hmm.
Or I could use these ratios again, 3:4, as TR, the small side, is to the bigger side. And then if you solve that, you'll notice that you're multiplying 3/4 times 24. So TR is 18. Okay?
Mm-hmm.
Basically going to do all of these the same. And the best way to do them is to figure out the linear area and volume ratio first thing, not last thing.
Mm-hmm.
So in this problem, what is here, they again give us the area ratio, which they say is 16 to 25. So what is the linear ratio going to be?
4 to 5.
Okay. And what's the volume ratio going to be?
64 to 125.
Yep. Notice the linear ratio is really close. It's 4 to 5, but by the time we get the volume of the bigger is almost twice the volume of the smaller.
Mm-hmm.
Now, from the figures they're showing us here, what are they talking about volume? But you can still talk about a volume of similar figures. In other words, we're only looking at areas here, so this R sub V doesn't make a whole lot of sense, but as long as you know how to find it. The area ratio is the linear squared, the volume ratio is the linear cubed. Okay, and now no, they're giving us the area. Well, let's see. No, they're not. They're telling what side is the same as PA.
ID or DI.
DI, exactly. In other words, the short top side of that trapezoid. This is a trapezoid. Okay? Trap is similar to zoid. That's pretty cute. So 4 is to A. What's A? Start with your linear ratio. In other words, 4 is to 5 as what is to what?
Would it be like 4 is to 5 as?
4 is to A.
Yeah.
In other words, we're trying to solve for A, right?
Mm-hmm.
What's A equal to?
5.
Uh-huh. Yes.
Oh.
No.
Okay.
4/5 has to equal 4/5. There's no other value for A that would make this a true equation other than 5. I mean, you can cross multiply it and solve it, but you should learn to kind of recognize when you have the same numerators and it's an equation, the denominators have to be the same also. Now, to figure out B, what am I going to say?
4th is equal to B over 8.
Make sure you get the little to big or big to little proper. You don't want to mix it up. The 4 over 5 is little to big. So you've got to make sure when you write this ratio, you write the same little to big. Well, little to big here is 8 is to B. 8's the small side, B is the big side. So if I solve this equation, I get a B of 10. And there's your A and your B for number 3. So far, we have not used the volume ratio, but I suspect we will. Still a good thing to calculate on every problem like we've been doing.
Mm-hmm.
Because at some point you will have to use it.
Yeah.
Okay, so here we have two similar semicircles. R is to S as 3 is to 5. Tell me R sub L.
3 to 5.
Tell me R sub A.
9 to 25.
And tell me R sub V.
27 to 125.
Now, they want the area. So they have given us the linear ratio. They want the area ratio. So give me the ratio equation that I can set up.
You could do 3 is to 5.
No, that's the linear ratio. We got to use the area ratio.
9 is to 25 as I have no clue.
Well,
R is to 75?
Which is the smaller one?
R.
Okay, so that's the area we're looking for, is the area of R, and it's got to go on top because you got to go little to big. And they've given us the area of of S is 75 pi. So that's all we're doing is we're setting up these ratios in the same order. In other words, it doesn't matter whether you go big to little or little to big, but we've been going little to big. Well, just make sure that the right side of your ratio is little to big. If you get it crossed, you're going to come up with the wrong answer. Okay, and then that number looks like 27 pi.
Yes.
And that's, centimeters squared. Whenever you're talking areas, you're going to be talking about square centimeters. Whenever you're talking linear measurements of any kind, you're talking centimeters. All right.
Okay.
I'm going to have to widen this to see it all. Lengths of corresponding diagonals of two similar kites are 3 to 9. What is the ratio of their areas? Well, gosh. I'm surprised that Yansak must be off his game a little bit.
He probably took this from another teacher.
What's that?
He probably took it from another teacher.
No, I'm surprised these are so easy.
Oh.
In other words, they're not getting tougher, they're getting easier. 5 is easier than 1 through 4. Because the lengths of the diagonals are in a ratio of 3 to 9. So the linear ratio is what?
3.
Simplify it if you can. Simplify it if you can.
Oh.
You certainly can, 1 to 3.
Yeah.
Okay. So what's the area ratio?
3 to 9? Or 1 to 9.
That means this kite, the smaller one, is 1/9 the area of this kite. Even though the diagonals are in a 1 to 3 ratio. So the ratio of their areas is 1 to 9. Okay. Now, let's look at number 6. We have two similar trapezoids, and they've given us the area ratio is 169 to 256. And they're asking us about the ratio of the lengths. Well, that's a linear ratio, right?
Mm-hmm.
And it doesn't matter what they could be asking about the height of the altitudes, they could be asking about the lengths of the base. Whenever they're asking about something that's going to be measured in centimeters, not square centimeters, then they're talking about a linear ratio. What is the linear ratio here?
It would be 13 to 16.
Yeah. So that's, in other words, he doesn't even ask any more after that. This is the equivalent of the first two steps on all of the previous problems. Not like him, to get easier.
It's okay though.
Yeah, really. Yeah, you don't mind it from your perspective. Let's see. Oh, here's another one. Okay, now we're going to deal with volume ratio. Okay, the length of the edges of two cubes are in a ratio of m to n. Tell me what the linear ratio is.
Oh, m to n.
What's the area ratio?
M squared to n squared.
That's that easy one. And the volume ratio would be m cubed divided by n cubed. Let's see. You only sent me one picture. We still have 10 minutes. You want to send me another picture, or do you have another one? Or
I do.
yeah, go ahead and send it. It doesn't take long to send it.
Okay.
Maybe we'll find some of his harder problems. Notice that all the problems we've had so far, when you took the square root of those fractions, you got nice whole numbers, right?
Mm-hmm.
Well, I had a Yancik student 2 years ago, and he gave out nothing but problems that had strange numbers that had no bearing to the other number, and you were always looking at a ratio that you then had to take the square root of, and you got a decimal, and the moment you get into decimals, that's when it's confusing to go little to big, and far less confusing to go big to little. That's why my preference is big to little, not little to big, because there are problems where if the numbers aren't just perfect, they become far more difficult when you go little to big.
You said that like he would most likely always have whole numbers, but I don't know if he's just telling me that.
I'm not sure that's true on these here, though. What I'm looking at here is not going to give you nice, even numbers. Okay. Mm-hmm. Here's the reason I'd rather go little to big. What's the square root of 4?
2.
What's the square root of 1/4?
1/2.
Yeah, but it wasn't as quick. It's harder to take the square root of numbers less than 1 because they get bigger. When you take the square roots of numbers bigger than 1, they get smaller. And so when you're going big to little, you're always dealing with numbers greater than 1. And it's very easy to take square roots of them, which you have to do a lot.
Mm-hmm.
See. And that's fine as long as he's given us ratios like 16 to 25. I can take square root of that without a calculator. But the moment he starts giving us numbers like this on number 11, then you end up with a ratio that's not so easy to take the square root of. Whereas if that ratio is a number bigger than 1, it would be very easy to take the square root of.
Mm-hmm.
All right, let's look at 8. Start with R sub L. What is R sub L? Little to big.
Would it be 4 to 7?
R sub A?
16 to 49.
And R sub V. Kind of come into play here because this is a three-dimensional object, so we're going to have to deal with R sub V at this point.
64 to 343.
243 is 7 cubed?
343.
343?
Mm-hmm.
Yeah, what's wrong with me? I knew that. Okay. And they give you the volume of the small pyramid. So give me the ratio I'm going to set up.
You do 64 is to 343. It is 320 is to H or X or whatever.
Yeah, exactly. Is the volume of the large. And then again, you don't have any problem solving these to come up with the answer. So let's set up another one. Let's go to 9. What's R sub L? Well, yeah, we don't know R sub L, but we've got our 3 things. What do they give us? They give us what?
R sub V.
R sub V, which is what?
12 and
12
7,
pi, that's a pi.
yeah, and then 768 pi.
Right.
I don't like
Could
pi.
reduce that. Obviously, those are even numbers, so I could certainly cut them both in half, but I'm not going to worry about it. It's not that big of a deal.
Yeah.
What is R sub L?
It would be 2 pi to...
Where are you getting that from?
I have no clue, actually.
Remember that R sub L is going to be the cube root of this ratio.
Oh, yeah.
So it's basically going to be this. 12 pi over 768 pi.
Yeah.
Not cubed, the cube root.
Yeah.
The volume is the linear cubed. So when they give you the volume ratio and they want the linear ratio, and they don't even want the linear, they want the area. But first we kind of need to figure out the linear. Okay? And what's the area ratio going to be? I might not know this, so let me write it. It's going to be the linear ratio squared, right? That's that. In other words, I'm taking this and squaring it. Well, when I square that, I do this. I put a 2 there. And now using the rules of exponents, you can multiply that 2 by the 1/3, and you get that to the 2/3. And what this means is the cube root of this, which would give you the linear ratio, and then we're going to square it with that 2. That's going to give you the area ratio. So finally, we have just about enough time for this. Give me a ratio that's going to allow me to answer the surface area of the small cone.
It would be like
You're going to need to convert that to a number. Okay? The pi's cancel. But take 12 divided by 768 and raise it to the 2/3 power, using parentheses around the 2 divided by 3.
Okay.
That's
And then you would do,
that's the fast way to do it. What'd you get?
I didn't get anything. What would you like?
Well, how would you get the cube root of that ratio? Let's get that first. Let's add the extra step. It's not 100% necessary, but until you understand the concept, you need that. So let's come up with this number right here. And all you need to do is into your calculator put 12 divided by 768, because the pi's cancel, and then raise that to the 1 divided by 3 power, like that.
Okay, so
What do you get?
I got 21.
Decimal is fine. A ratio would actually be probably a little better, but a decimal's okay.
It's like 21.3. It would be like 21 and 1/3.
No. You went big.
Okay.
You went big to little, or you didn't put it in your calculator right. In other words, I know this number is going to get bigger when I take the cube root of it, but it's not going to be bigger than 1. In other words, there's no way the volume ratio can be 12 to 768 and have the linear ratio be a number greater than 1. It's still got to be little to big.
I have it. It's 0.005. I don't know if that works.
Let's see. If we had 1 over 76, that's about 0.02. That doesn't sound right. Here, let me put it into Wolfram Alpha. I'm not sure. You have a TI-84? What kind of calculator do you have?
I mean, it's not mine because my brother stole mine, so it's a TI-84 Plus.
Okay.
It's pretty old.
That's fine, but that'll certainly get the job done. So here's the way I want to put it.
Yeah.
12 divided by 768, in parentheses, all of it, raised to the, in parentheses, 1/3. That's taking the cube root of that ratio.
Okay.
And the answer is 0.25. They just told it to me.
Okay.
In other words, yeah, it's 1/4 exactly. So he did give us good numbers. So it's not 0.05, it's 0.25.
Okay.
Now, what's the area ratio? The area ratio is what relative to the linear ratio?
It would be 0.25 squared.
Which is?
0.0625. So it'd be 1/8. Or, right?
Not 1/8, 1/16.
Oh.
Not 1 is...
Close enough.
Because remember, this is 1:4. This one has to be the square of this one.
Mm-hmm.
Okay. Now, in this particular problem, give me the final step. What's the ratio?
So it'd be 1/16 to
Equals. It's
equals
1 is to 16 equals what?
it would be x over 384.
384 pi. Don't forget the pi. You probably lose points if you left the pi out. In other words, x is going to be in terms of pi also. But basically, you're going to take 384 pi divided by 16. That's what x is going to be. Okay? So all of these are the same. And it looks like even these big numbers that he's giving you here are going to have nice square roots. Like this, I had no idea the square root of that was going to be 1 to 4. Okay? Now, I didn't technically have to do that step. notice that if I would have merely taken that and taken it to the 2/3 power, I would have immediately gotten 1/16. In other words, I really at no point in this problem needed the linear ratio. You can go straight from volume ratio to area ratio by raising the ratio to the 2/3 power. You don't have to do it that way. Probably the way that avoids the most mistakes is to do it exactly the way they suggest, which is to go ahead and do the linear ratio and then the area ratio and then the volume ratio, and make sure that they're in the proper relationship. In other words, make sure the area ratio is the square of the linear.
Okay.
But all of these are going to be the same. This back page, you're going to use the volume ratio a lot more than we did on the front page, which was to say nil. But I think you can figure out how to do the rest.
Okay.
Okay? All right, Ali, I will talk to you next Tuesday and next Thursday, right? You want both sets?
Mm-hmm.
Okay.
Yeah.
Talk to you Tuesday.
Thank you. Bye.